Okay, so here's just another way of displaying that, basically that same information. But this also goes a little bit further. It has more unsaturated fatty acids. For instance, it shows DHA, EPA, nervonic acid, and what those melting points are. Okay, so the next thing that I want to get into is kind of that nomenclature. We've already talked about the omega system, but now I want to talk about this delta system. This delta system is another way in which you can extract some information about double bonds. Now, these are all 18 carbon long fatty acids. These are the same stearic acid, oleic, linoleic, and alpha-linolenic fatty acids. We have a delta 9, which shows that there's a double bond between carbons number 9 and 10. But this N-9, that is showing the same thing. Now the difference between these is that this numbering from our carboxylic acid. Okay, and this is numbering from our omega fatty acid. Okay, so as it turns out, this example is an 18 carbon long fatty acid. Whether you're starting from carbon number 1 or carbon number 18, the number 9 position is going to actually show the double bond in the exact same place. The difference is that when we start numbering, so it's almost like a thing of perspective. So this fatty acid right here, this oleic acid, is both this and it's this. Okay, so I think whenever you look at a different fatty acid, say a 16 carbon long fatty acid, well, you can delta 9 and N-9 are going to show different things whenever you're looking at a 16 carbon long fatty acid. Now, with that said, let's look at our other two, linoleic acid and alpha-linolenic acid. Oh, sorry, my writing there. Linoleic acid C18:2 delta 9 comma delta 12. Okay, whereas with the omega system it would be C18:2 omega minus 6, because 1, 2, 3, and I'm writing the numbers for the omega system, 4, 5, 6. Now, one thing that's significant about this is we only show the information for the first double bond. The reason for that is because we can default to believe that these double bonds are in the cis position and they are non-conjugated. So we can expect double bond, single, single, double. Okay. So if you want to compare these two systems, is there one that is more kind of explicit? Absolutely. That delta system shows exactly where all of the double bonds are. As we see here when we talk about linoleic acid. Linoleic acid shows us our double bond, or all of our double bonds, delta 9, delta 12, delta 15, whereas the omega system is 18:3 and minus 3. So these are showing the exact same thing, but it just displays it in a slightly different manner. So it's all about perspective and orientation. What carbon are you starting from, the carboxylic acid or the omega carbon? So generally, whenever you talk about fatty acids, you're talking about triacylglycerols, because that's the closest to the polymer that they can exist in. Triacylglycerols or triglycerides. Triacylglycerols are triesters of glycerol. So you take your kind of foundational molecule right here of glycerol, and you have 3 hydroxide groups that you can basically use as foundation for an esterification reaction, in which case you can add these at the carboxylic end of your fatty acids to that OH group. Most are going to contain 2 or 3 different types of fatty acid residues. So here's an example: 1 palmitoyl, 2 linoleal, 3 stearoyl glycerol. And so we've got palmitic acid and then 2 18 carbon long fatty acids. The linoleal and stearoyl glycerol molecules are going to be esterified to there as well. So that's basically your largest I guess kind of or your closest thing to a polymer, but keep in mind that fatty acids do not polymerize. Instead, you undergo the esterification reaction where you can have multiple of these molecules on one. Okay, so the way it goes kind of from a nutritional standpoint is that many animal fats are going to have a high percentage of saturated fatty acids, in which case we look at beef fat over here. Beef fat at room temperature is generally going to be a solid. Keep in mind, those individual saturated fatty acids, they're going to pack very well together. And the vast majority of them are going to be in the 16 to 18 carbon length saturated fatty acids. There are some unsaturated fatty acids, but again, animal fats are largely going to be 16 to 18 carbons long. When it comes to plant fats, so like olive oil, for instance, olive oil has a high percentage of unsaturated fatty acids right here. And so what that's going to be at 25 degrees or close to room temperature, that's going to be a liquid because of that high concentration or high percentage of unsaturated fatty acids. In all three of these cases, beef fat, olive oil, and butter, you have a very low percentage of short fatty acids ranging from 4 to 14 carbons long. That's that last chunk down here at the end. There, and there. Okay. Now, the biological role of triacylglycerols is they're largely going to be serving as an energy reservoir or an energy source. The fat content of humans allows them to survive for 2 to 3 months without the input of any other carbohydrates or any other fuel sources. So basically, you have at any given moment a very large percentage of fats that can be broken down. Now, in addition to that, triacylglycerols are going to serve to insulate and protect. Olestra is one thing that's just kind of brought up as like a little bit of a sidebar. That was a non-hydrolyzable fat that was developed in the, I'm not exactly sure when it was developed, but it was deployed onto the food market in the mid-90s. It was a carbohydrate-based fat that you couldn't really metabolize, and that was something that was used in Wow brand chips for quite some time. But at any rate, I'd like to show this because here's our triacylglycerol molecule. Now that triacylglycerol is going to undergo one of two processes. It's either going to be enzymatically hydrolyzed or it's going to undergo saponification. Okay, so saponification is an industrial process. If you've ever seen the movie or read the book Fight Club, saponification is a key part of, well, it's not a key part, but it's a part of that movie where they take animal fats and convert them into soap. And so what you do with this is you're going to generate glycerol. You're going to take your triacylglycerol, treat it with aqueous sodium hydroxide, and break that triacylglycerol into free fatty acids as well as sodium ions. So it's going to make a sodium salt of a fatty acid. Enzymatically, the way that triacylglycerols are processed is that you have an enzyme known as a lipase. And what a lipase does is it's going to produce that glycerol molecule, but it's not going to generate a sodium salt, but rather it's just going to break that ester bond between your fatty acid and your glycerol molecule, and it's going to produce an ionized fatty acid. All right, well, I hope this is helpful, and I will see you in the next portion of lipids discussion. Thank you very much. Have a good one.